Hello everybody and welcome back to Calculosity. It's your host Corey, and today we're going to be discussing how to algebraically calculate limits. Now previously we discussed how to do so graphically by taking our fingers and tracing along a function and figuring out what y value we are approaching. But here, things are a little bit different. Now we're going to have to figure out without graphing anything. Now, for those of you who are not so graphically inclined and who prefer to work with numbers and just numbers, this is going to be a little bit easier for you, but we're still going to look at a couple graphs as well to try to make some sense of it. So, for today's lesson, let's consider a function. Y equals x squared, and why don't we choose some value like plus 5. So what this function is it is a function that is graphically going to look like this. It's going to look like I should probably draw this a little bit differently. It's going to look like a normal parabola, but it's going to have its vertex at y equals 5. So it's going to look something like this. And it's going to have y equals 5 there. So we want to consider this algebraically. So previously we'd note that as we go towards x equals infinity, the parabola is going to go towards y equals infinity. And as we go towards x equals negative infinity, y is going to equal infinity yet again. That's because when we trace it with our fingers, we're going off into the infinite beyond. Well, now we have to figure out what happens algebraically and how to calculate that. So it's going to be helpful for us to use an important bit of notation that is y is equal to f of x. We use this quite a bit. Now forgive my terrible handwriting, but we use this quite a bit just as a better way to represent functions of a specific variable. Now y is great, but y is very, very vague when it comes to what we're plugging into a function. So with this notation now, we can figure out what the limit of f of x as x approaches any given value. So let's look as x approaches 0 in this case, which is right where the y-axis meets the x-axis, the origin. So let's look at x equals 0 of this function. Now we're going to want to write this out with the actual function in mind. This is how you're going to see it most of the time, which is the limit of x squared plus 5, the actual f of x function substituted in for f of x as x approaches 0. So now all we're really going to have to do, because we can tell intuitively that if we were to run our fingers along this graph and work our way on either side towards x equals 0, we can see that we're getting to y equals 5. That's intuitive, right? And our fingers on either side of this graph are going to meet when they get to x equals 0 at y equals 5. So that means that this limit is supposed to equal 5, and that's intuitively because the actual function at x equals 0 is equal to 0 squared plus 5, which is 5. So we're going to find that any normal behaving function that doesn't have any weird stuff, no asymptotes, no vertical or no discontinuities, no jumps, no steps, etc., 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 anything that functions normally and is a regular function with no issues, no division by 0, no square roots of negatives, no logs of zeros or negatives, any function like that, there's a really simple way to calculate these limits, and that's just by plugging in that limit value into the function. So here, as the limit of f of x as x approaches 0 is actually going to be equivalent to f of 0. Super intuitive because our fingers are going to move towards that point. And so, that is how we'd algebraically find a limit at a x approaching a finite number in a well-behaving function. Now later on we will go into not so well-behaving functions and how to algebraically solve them. So in a well-behaving function, this is what we're dealing with. Now, that's great. We found out a finite number approaching a finite number. Woo! Not from the left, not from the right, but just generally. So let's think a little bit about the left and the right. Now in our previous video, I mentioned several times that the limit of f of x without any sidedness, that means not coming from the left, not coming from the right, if this is not, or rather if the left does not equal the right, this limit is going to be dne, does not exist. But since this limit does exist, and it's f of 0, which is 5, since it does exist, that infers thus, I should have drawn a bijection, which means that either side infers the other side. I should have said that this infers that the limit on the right side as x approaches 0 is equal to the limit on the left side of x approaches 0. Which is equal to a. So, if a equals this, then those two are also going to be equal to a. So by this, we can actually figure out quite easily what the left and right-handed solutions are, because they're going to be exactly the same. The idea here, to sum it up, is if the limit exists from both sides, if the limit exists without any sidedness, so x approaches 0, then from any side it's still going to be the same value. So thus, since this guy, our x approaches 0 generally is 5, then so are the left and the right limits. They're all 5, because they have to match. Now, let's consider this same function, the parabola, x squared plus 5. But now let's look at the infinite limits and see how we can calculate those by hand. So, let's see. The limit of f of x as x approaches infinity. Now previously we saw that we could do f of a. We could plug in that value that the x is approaching. Like before we said limit of f of x as x approaches 0, f of 0. Now we can say that the limit of f of x as x approaches infinity. Oh, I should have drawn an arrow, my bad. That is kind of sort of, I wouldn't write it like this necessarily, but we can think of it as f of infinity, just like we thought of f of 0. And so if we did the actual math here and we were trying to figure out the limit of x squared plus 5 as x approaches infinity, well, if this is f of infinity, then this is going to be infinity squared plus 5. That's pretty intuitive. Infinity squared is still going to be a really, 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 really large number. And so it's going to be infinity plus 5. But remember, infinity is an extremely large number. 10,000, 1,000,000, 1 sextillion. We add 5 to that, it's pretty insignificant. In fact, it's pretty much null. So for that, infinity plus 5, infinity plus anything is going to be still infinity. As a result, the limit as x approaches infinity is infinity. And we can see graphically that that is sensible. As we move off into the x equals infinity direction, our y values are getting larger and larger and larger, moving towards infinity on the graph. And so this should be in agreement. And the same kind of argument comes from negative infinity. If we want to deal with that, we'll extend our line a little further down here. Now if we're dealing with negative infinity, it's going to be the same concept. Now we're going to do the limit of f of x. Here we are. Limit of f of x as x approaches negative infinity. That's going to be the same as kind of sort of plugging in f equals negative infinity. Now that's not great notation because negative infinity is not a value, but this notation does make some sense in that you have to plug in kind of sort of negative infinity. And you can think of it as, say, plugging in negative 1 million, negative 10 million, 10 billion. It's all pretty intuitive. So by that then we're going to plug in this really, really, really negative number into this function. And so that's going to be negative infinity, make sure you use parentheses, very important, squared plus 5. Remember, any negative value squared is going to be positive. Negative value times a negative value is going to be positive. So this is going to result in infinity squared, which is infinity as we discussed in the last problem, infinity plus 5, which is still infinity. So there you have it, the algebra agrees. But the algebra is not always so nice, unfortunately. So let's look at a function that is not always so nice. Right, so let's dig into that. We're going to think of another function here. Oh, I should probably draw it a little bit differently. We'll think of this function. The function is going to be x equals, or rather y equals 1 over x. It's going to look like that. 1 over x is problematic because you see there is an asymptote, a vertical asymptote at x equals 0. This guy right here never touches the line x equals 0 because it is a vertical asymptote. Why that is? It's because you can't plug in 0 for x. If you did, you'd get 1 over 0. And if you've ever used a calculator and tried to plug in 1 divided by 0 or anything divided by 0, you will get the error, cannot divide by 0. And that kind of behavior causes the graph to look like this. As we get closer and closer to 0, we're dividing by a smaller and smaller number. And when we divide 1 by 0.000001, we get 1 million, or something to that nature. The more decimal places we move that 1 over, we get an even larger number, like 1 billion, 1 sextillion. So, as a result, we get these massively large, negative and positive integers or values, period. And that causes this kind of behavior on the graph. So now what if we want to find some limits of this? Well, let's first consider the limit as x approaches 0. Like we see, there's some weird behavior going on there. So we want to understand how we can represent this behavior, which we already know from the previous lesson results in a does not exist for the general limit. That is because the left-hand limit is negative infinity and the right-hand limit is infinity, and since they don't match, our limit does not exist. So let's see how that looks algebraically. So we want to find the limit of this function. We're going to call this function g of x. So we want to find the limit of g of x as x approaches 0. Which, remember, is the limit of 1 over x as x approaches 0. If we do the plugging in, we're going to get this as our answer, 1 over 0. Dividing by 0 is a no-go, not acceptable. And you know what that means? That means that the limit does not exist. Anytime we get division by 0, the limit does not exist. This is important. Any integer over 0 does not exist. Remember it. Very important. Because you're going to encounter other examples in which this happens. We can think of the same exact function, 5 over x. It's going to look a little bit different, a little stretchier, but it's going to have the same exact behavior at x equals 0, and it's going to result in 5 over 0, which is still dne. So anytime you get an integer over 0, an integer not equal to 0 over 0, it's dne. The only time this is not the case is when you get 0 over 0. That is something that we will discuss later. That is not dne. That means something else. So this is how we see dne represented algebraically. Let's look at the end behavior of these guys, right? The end behavior is what goes on as we go towards infinity and negative infinity. That is considered end behavior. Yet again, my handwriting is horrible. Please don't judge me. So that's going to be our end behavior. That's what happens as, well, we move towards the ends of the function at this end and on the other end as well, as we go towards positive and negative infinity. Alright, so we want to look at the end behavior now. That is going to be notated as we did in the previous problem with the parabola. That's going to be as we go towards x equals infinity or negative infinity. So let's look at x equals infinity. We're going to plug that in like we did in the previous problem, and we get 1 over infinity. Oh boy, now what does that mean? Think of the numbers. Remember, I said that you can consider infinity to be 1 billion, 1 sextillion, something really large. Well, if you plugged into your calculator 1 over 1 million, which is still a rather small number, but it'll work for this particular example. If we plugged in 1 over 1 million, we're going to get a ridiculously small number, which is 0.000, several zeros, and then we're going to get a 1. This is super small, and it is very close to 0. And you're going to find that anytime you divide 1, or really any number, by a ridiculously large number, we're going to get something that is very close to 0. As a result, since this is about equal to 0, that's what that equal sign with the curls means, about equal to 0, we can pretty well conjecture that 1 over infinity is actually going to be equal to 0. And you're going to see this a lot of places. This is very important as well, that 1 over infinity equals 0 when it comes to limits. Very important. So don't forget that as well. Just like 1 over 0 equals dne. And the same thing will occur if we did the other side. The distinction here is if we did the other side, we would get 1 over negative infinity, which is still 0. Why that is? It's because it's going to be negative 0.0000001. But even though it's negative, it's very close to 0 nonetheless. So it's still going to be equal to 0. Alright. So that's how that looks. The only distinction now that we have to really concern ourselves with is weird behaving functions that have things like steps and jumps and discontinuities and things. But we haven't discussed what discontinuity is yet, but there is no reason why we cannot look into functions that behave a little bit strangely and still have these yet to be discussed discontinuities. Points at which the function is not continuous, as in there's a gap. We already discussed asymptotes are a type of discontinuity. And we've already mentioned jumps, which are another type of discontinuity. So what happens if we try to calculate a limit on a function that has a jump? Well, here's the issue. There aren't really any functions that have jumps. There are some functions like the floor function that produces jumps. The floor function is a jumpy function. It's going to give you something that looks jagged, like so. It'll give you something like that. Problem is, the floor function isn't really anything that we're going to encounter so often when we're working in math. So, as a result, we're not going to worry so much about these discontinuities until later. But we do have something that we can still consider. And what that is it is called a removable discontinuity. Yet again, we have not discussed continuity yet, but in the case of a removable discontinuity, we encounter something very special. So this will be a little preview to what we're going to go into in a couple episodes. And that is if we have a function like this, that is y is equal to a function that, say, x plus 1 x over x plus 1 x minus 1, something like this. This function is actually going to be given to you in a different form. It's going to be given to you as x squared plus x over x squared minus 1. That's what they'll give to you. You'll have to figure out that there's an x plus 1 in the numerator and an x plus 1 in the denominator, and you're going to have to cancel them. But after you cancel them, you see, you end up with x divided by x minus 1. That is a better behaving function. But if we try to do the limit on the function in its native form, now the point of weird behavior here we should be able to assume is going to be x equals negative 1. That's when the x plus 1 is 0. That causes things like division by 0. So let's look at the limit of this function, x plus 1 x divided by x plus 1 x minus 1, as x approaches negative 1. So if we were to do what we usually do, which is plug directly in, we get something weird. The numerator, x plus 1, becomes a 0. The denominator, x plus 1, becomes a 0, times negative 2, which is still 0. That's 0 over 0. Now remember before, I said 0 over 1, or sorry, 1 over 0 is g and e. 0 over 0 is not. 0 over 0 is what they call an indeterminate form. Indeterminate. And an indeterminate form means exactly what the word says. It's not determinate. It doesn't determine anything. We need to take it a step further. So anytime you see an indeterminate form like that, you need to simplify. This is important. If you encounter an indeterminate form, it means there is some way to simplify the function and to get an answer. Because what happens is, a function that looks like this looks like this. This may not be that exact function, but it looks like this. It has a hole in the middle. But if we know anything about limits, if we still ride along the side of this value with our tick marks, we're going to get this y value, which could be an a. And if we ride along the other side, we're still going to get the same exact value. And because the left and the right are equivalent, the left equals the right, the limit exists. The limit exists, and when I say the limit exists, I mean the limit that doesn't have any sidedness. The limit exists, and it's equal to a. This is what we're dealing with. If we did it without simplifying, it would be 0 over 0, indeterminate. But with simplifying, we do what is called removing the discontinuity. This is known as a removable discontinuity. We pluck it out by canceling out that x plus 1 over x plus 1. And we get the function that is underlying that does not have a hole in it. And that enables us to plug directly in the function value and not get any weird behavior. So now, what we can do on that previous function is we saw previously that is equal to x divided by x minus 1. That is the equivalent function, but it does not have a hole in it. So y equals x divided by x plus 1. Now we can find the limit of that easily at x equals, or rather, sorry, it's x over x minus 1. We all make mistakes. So x over x minus 1 at x equals -1. We can plug in now and see that that would be -1 divided by -1 minus 1. And that is -1 over -2, which is just 1/2. And that is the actual answer. You have to simplify when you get an indeterminate form, and it will give you a right answer. Unlike when you get a does not exist form, which is 1 over 0. That will never simplify to get you an answer. This does have an answer. And so, that is what is considered a removable discontinuity. And so, that being said, we have now discussed how to calculate the limit algebraically, whether it have a discontinuity, like removable, or an asymptote, whether it gives you an indeterminate form or a determinate form or does not exist. And now, without graphs, we can solve by simply plugging that value into the original function to calculate its limit. Remember, the most important part is always going to be that the limit of f of x is equal to f at that a value. That limit of f of x as x approaches a is going to be equal to f of a. If you don't forget that, you should be able to pretty safely calculate the limit on most basic, well-behaving functions. And so there we have it. We've completed another step.